Good morning, ladies and gentlemen. Welcome to the properties of multiple distributions, and this is where probability starts getting really very tough. So there are three rules here, and then there's three more below. So these multiple distributions occur when we have multiple different sets of x, which means outcome distributions, outcomes and probabilities under each other. What happens when we combine different distributions together? And we'll use a dice example for lots of this. So remember, the expected outcome of a single dice roll is 3.5, and each one of those dice rolls has an equal chance of occurring. So these three rules essentially say this. The expected value of k for any constant k. Imagine if you had a dice with all sides equal to 4. The expected value for that dice would be equal to 4. 4 on the dice is constant, so anything here that has a distribution with the same value all the way up the top, 4, 4, 4, 4, 4, 4, etc., is going to have a constant expected value. And that's essentially what the first rule is saying. Makes a lot of sense. All right. What this one here is saying is that the expected value of k times x. So remember, x here for us is going to be a dice, 1, 2, 3, 4, 5, 6, and then a sixth, a sixth, a sixth, a sixth. And we know that the expected value for that is equal to 3.5. Bang in the middle there. All right. What's happening here is it's saying we multiply each one of those numbers by a certain constant, k. So let's say we have a dice that instead of reading 1, 2, 3, 4, 5, 6, reads 3, 6, 9, 12, 15, 18. Essentially, every face of the dice has just been multiplied by 3. Rather than having to recalculate the expected value by hand long ways, we can say that, well, if every value is multiplied by 3, it must be 3 times the original value. So the expected value of x is just 3 times what we had previously. 3 times 3.5. So what's that? 10.5. So the expected value now would be 10.5. And we can see that still fits right in the middle there. 1.5 up from 9, 1.5 down from 12. Right. So if every term inside a distribution is being multiplied by a constant, that has the same effect of multiplying the expected value, or the average, by that constant. I hope that makes some sense. This is what's happening here. If we have two distributions put together, let's think of this as dice 1, and dice 2. The expected value of dice 1 plus dice 2 is equal to the expected value of dice 1 plus the expected value of dice 2. Let's say they're both ordinary dice. The expected value of a sum of dice is equal to the expected value of one dice plus the expected value of the other dice. What that's saying is if you roll 2 dice and add them together, the expected value for that addition is 7. Or, another different way of thinking about this, if we have different dice. Let's say we have one ordinary dice, and then we have this red dice over here. So, dr, the red dice. The one that's every term's been multiplied by 3. This red dice looks like 3, 6, 9, 12, 15, 18. Alright? The expected outcome for the sum of those two distributions, or sum of those two dice rolls, would be 3.5 from the normal dice and 10.5 from our special dice, leaving us with a grand total of 14. We would expect the average return to be 14. Alright. We'll put these rules into practice and spend some time putting them into practice, but now I'd like to go on with a slightly different and more complex one. Alright, so consider this example. Just looking at part A for now, so ignore everything under that red line. We want to find the expected variable, the variance, and the standard deviation for x, where x is above. And x is a uniform distribution with possible outcomes 1 to 5, and each one having the same 0.2 chance. So we should know straight away that the middle value, 3, is going to be the expected one. But we can also use our calculator, remember. So here is the calculator, and we want to settings, variable list, list 1, they're the variables, frequency list is list 2, they're the frequencies, or the probabilities, and we press one variable. And unsurprisingly, the variance, or average, is 3. The standard deviation is, well, that actually is root 2, which is quite nice. So here, the variance is, sorry, the expected value is 3, standard deviation is root 2, variance is just going to be 2. Alright, now, let's look at what happens when we adjust this distribution. And adjusting the distribution looks like this. New distribution y is equal to 2 times the previous distribution plus 3. 2 times the previous distribution plus 3 is saying, well, 2 times 1 plus 3 gets us to 5. 2 times 2 plus 3 gets us to 7, etc. Note how this here hasn't changed the probabilities of each of the outcomes, but the outcomes have changed. Alright? So now, let's find the new variance, standard deviation, and expectation, and see how if we can relate them to the other ones. Alright? If you want to think about this a little intuitively before we start, what we should be thinking is, well, if the mean of this was 3, the mean of this one should be 9. So that there, well, what's happened? And we'll look at that in a sec. Rather than doing this by hand, we can enter on the calculator. Note how I have the other outcomes here. 5, 7, 9, 11. Rather than writing over list 1, what I can do is write in list 3 and change the settings and change the X bar list from list 1 to list 3. And then recalculate. And here, the expected value is 9. And the standard deviation is 2 root 2. Variance there being standard deviation squared. Well, if you square that, you get what? 4 times 2 is 8. 8. No, 4. Bear with me. Brain's not working. 2 squared times 2 is, 8. Alright. So, what's the relationship between these two? These rules should give us a hint. If we take the expected value of an adjusted distribution, ax plus b, in our case here, 2x plus 3, that should be a times ex, so a times the original expected value, plus b. Now the original expected one was 3, so we're thinking here that this will be 2 times 3 plus 3 is equal to 9, and that's what got us to here. The variance will be a squared times the original variation. Here a is 2, and the original variance was 2. So this here looks like a squared is 2 squared times 2 equals 8. Now here, standard deviation is mod x, mod a. Mod a is, I'm not sure if you've seen this before, but the modulus of a, or the absolute value, meaning the positive size, or positive value, pos value of a. So a here was 2, but even if it was minus 2, we'd still write 2 when doing this. Is just 2 root 2. Alright, a few things to notice. Firstly, b is changes where the expected value will be, or where the middle will be. But note b on the end doesn't increase the spread of the data. So by adding 3 to each data point, so adding 3 to each of these, wouldn't increase how spread out they are. Which is why adding 3 to them, or the b part, doesn't play any part in the variation, or the standard deviation. What does play a part is a, because we multiply say, each of them by 2, multiplying by them by 2 increases the spread between the top and the bottom. Multiplying it by 10 would increase the spread even more, which is why here A plays a part in calculating the new variance of the distribution. Alright, that's the only example I want to go through. We will do more in class, of course. But as long as you're comfortable that we can take a distribution, modify it with a multiple distribution, and then use these rules to work out the new expected value and the new variance based on the previous distribution. And then, of course, later on, because it's methods and we want to make it even harder, is they'll expect you to combine these rules with what happens when we throw multiple different sets together. Right. But we'll do more of that in class. Thank you very much.